So our topic for today is confidence intervals derived from a large sample normal approximation to the sampling distribution of a maximum likelihood estimator. And so I wanted to just take this first video to motivate our reason for doing this, or like why we have to do this idea. And in order to do that, I want to start off by just reminding us of the procedures for deriving confidence intervals that we talked about over the last couple of classes. So we have this procedure for deriving confidence intervals that has 3 steps. And the first step is to identify a relevant pivotal quantity. And find its distribution. In the examples that we looked at last couple of classes, we had 2 settings, both of them based on a normal distribution. And our first was a pivotal quantity T equals capital X bar minus mu over capital S over square root of n. And this follows a T distribution with n minus 1 degrees of freedom. Or I'm using the letter T here for a statistic generally, not necessarily just a T statistic. So another example, I'm just going to call it T, even though it's not a T random variable, equals n minus 1 S squared over sigma squared, which follows a chi-square distribution with n minus 1 degrees of freedom. So we identified these 2 pivotal quantities. Both of them involve the data x1 through xn. And the first one involves the parameter mu. That's a parameter that we're trying to get a confidence interval for. The second one, the confidence interval we're aiming for, is sigma squared, so that involves the sigma squared in there. In both cases, someone has derived the distribution of this statistic, and it depends on things like a degrees of freedom maybe, but it does not depend on unknown parameters. So this is the essential first step for deriving a confidence interval. And once you have that, you can take quantiles of the distribution of the statistic. Or not really the statistic, of the pivotal quantity T. And then 3, you have the probability statement coming out of step 2, and then in step 3, you rearrange and do a little algebra to get a statement like probability that A is less than or equal to whatever your parameter is, theta, is less than or equal to B is 1 minus alpha. And then A, B is your interval that you were looking for, a 1 minus alpha times 100% confidence interval. So this is the basic procedure for deriving confidence intervals, and this is not going to change. This is going to stay the same. The problem is that this first step is really hard. Finding a relevant pivotal quantity, I guess that's actually not so hard. Like, it's easy to make up a pivotal quantity, like almost always something of the form like a T statistic will work. But the challenge is that it's not always easy or even possible to find its distribution. And you need to find its distribution in order to be able to take quantiles in step 2 and move forward with the confidence interval. So really, this part right here is hard and not even always possible. So what we need, as always, is what do we do when things are hard? We do approximations. So in simple problems, I feel like there almost are no simple problems, but in the simple problems that exist, it's possible to derive a distribution of a relevant pivotal quantity. That's actually the exception. Like more often than not, you can't derive a pivotal quantity and figure out what its distribution is. So in those cases, we need approximations. So when we can't find the sampling distribution of the pivotal quantity, what do? We approximate it. And there are, as always, basically two approaches to doing that approximation. So we can use one of two ideas. The first, which is what we're looking at today, is a large sample normal approximation. And this is sometimes referred to as a walled interval, the result of this. And the second approach is going to be computational. So a computational sampling based approach. And the main idea here is the bootstrap. So we're going to look at idea one here today, and then over the next following couple of classes, we'll look at the bootstrap.